Hi everyone. In the previous class, we have seen the advantages of closure set of attributes. Right? So, what are the various kind of advantages of the closure set of attributes? One is we can able to find out additional functional dependencies. Right? The another one is we can able to define whether two independent functional dependency sets are equivalence or not. The another advantage of this closed set of attributes is we can able to find out whether a particular attribute is a candidate key or not, meaning that we can able to simply find out various kind of candidate keys for the given relation. Similarly, we can able to find the irreducible set of functional dependencies. Right? These are the various kind of advantages that we have seen with various examples. So what is the meaning of irreducible set of functional dependencies? If you are going to have a set of total functional dependencies, among those functional dependencies, sometimes there is a chance of getting a redundant functional dependencies also. If you are going to remove these redundant functional dependencies, what are the result that we are going to get? We can call it as irreducible set of FDs. Right? Yes. And candidate key means which is a kind of a key which can able to identify the tuples uniquely in the entire table, right? So basically, if a table having more than one primary key, then all those keys I can call it as candidate key. Equivalence means what? If F is going to cover G as well as G is going to cover F, I can call it as equivalence of FDs for both F and G. Additional functional dependency means if we are going to have a set of functional dependencies F1, if you would like to find out some other functional dependencies like F2, with the help of inference rules we can able to get, or with the help of closed set of attributes we can able to get. Right? This is what we have seen earlier classes, and also we have seen the various drawbacks of bad schema. If you remembered it clearly, that one of the drawback of the bad schema is it can able to produce the vast redundant data, right? So, and also it can able to generate various kind of anomalies that can be insertion anomaly, updation anomaly, or deletion anomaly, like that, right? Similarly, when you are going to combine two or more tables, it may generate lossy data. These are some of the problems that we are going to face if you are going to design any kind of bad schema. So, to overcome these drawbacks, we have seen various kind of features also, but to eradicate these completely, we need to go for a kind of a concept called functional dependencies, right? So that is the reason we discussed various kind of functional dependencies. Like with the help of these functional dependencies, we can able to define simply the relationship between the attributes, right? Relationship between the attributes, so that we can able to define what attributes are redundant, what attributes are not redundant, and how we have to make the keys. All those things we can able to define with the help of functional dependencies, right? And then also we have to use one more concept to eradicate the redundancy by using the concept of normalization. See guys, normalization means it's a kind of decomposing a single table into multiple tables, guys, into multiple tables. So if you are going to remember certain kind of examples where, for example, if I try to say any kind of a table called J, K, L, it's a kind of a schema. This schema I am going to split into two tables. One is J, K is one kind of a table. Another table is J and L. Right? So this is what I can call it as normalization. But while doing the normalization, you have to take care of many factors that we'll see in the further classes. Right? So this is what you can call as normalization. So with the help of this normalization, we can able to reduce the redundancy. We cannot say that complete redundancy we can eliminate, but we can reduce the somewhat redundancy, right? Yes. And also we have introduced a concept called lossless decomposition. Okay, fine. So I mean, basically guys, client is going to give various kind of requirements. These requirements are going to taken care by the designer, and he will define various kind of FDs with help of his basic thinking, that is F2, and with help of closed set of attributes or with the help of inferences he can able to find out the set of other additional functional dependencies, and we may call the both F1 and F2 as total functional dependencies, and then he may generate various kind of tables in order to reduce various kind of redundancy factors, right? Yes guys, we generated the tables. Once we generated the tables, like assume that T1 is one table, T2 is one table, T3 is one table, and so on. Various kind of Tn tables are there, right? So these tables, if you are going to combine again, you have to get the actual table data. For that, we need to know the concept of lossless decomposition concept. What I am trying to say is, so if I am saying that it is a kind of a lossless decomposition, when you are going to combine multiple tables, multiple subtables into single table, that single table contains the actual rows, then I can call it as lossless decomposition. Otherwise I can call it as lossy decomposition, guys. Okay, if you are unable to understand this definition clearly, after few minutes of time you can able to understand what is the meaning of lossless decomposition with help of simple mathematical notation. Okay, before going for that, let me take a simple example. For example, I am going to have a table called JKL, and suppose for example it is going to have certain data. Assume that A1, B1, C1, or A2, B2, C2, A3, B1 and C3. Guys, assume that this is my data is there. So this is actual table, I can call it as R. Now my requirement is, in certain kind of conditions, with help of certain kind of procedure, I splitted this table into two tables. One is J table. I mean, it contains a table attribute called J attribute, and the other table contains an attribute called K and L. This one I can call it as R1, and this one I will call it as R2, right? So if I am going to make it splitting the data, you can get in the J attribute column as A1, A2, A3, and in KL you are going to get B1, C1, B2, C2, and B1, C3. Guys, why I try to reduce this particular form? Because to avoid the redundancy data. Right? As a very simple example, you cannot able to understand like how you are eliminated the redundancy, right? If you are able to understand the earlier classes, you can able to understand how we eradicate the redundancy, right? Yes. But try to observe, after decomposing a single table into two tables, if I am going to combine again these two tables, what data you are getting here? Observe, I am going to make A1 is going to combine with B1 C1, A1 is going to combine with B2 C2, A1 is going to combine with B1 C1. Similarly, A2 B1 C1, A2 B2 C2, A2 B1 C3. Similarly, A3 B1 C1, A3 B2 C2, A3 B1 C3. So this is the resultant relation you are going to be generated, right? So if you are able to observe, so the resultant contains A1 B1 C1. See, I will take some other color. A1 B1 C1, A1 B2 C2, A1 B1 C3. Okay, so like this you are going to get various tuples for the A1, B2 C2, A1 B1 C3. This is for A1. For A2, what will happen again? A2 B1 C1, A2 B2 C2. Similarly, A2 B1 C3. See guys, this is for A2. Similarly, for A3 also, you are going to get 3 more tuples, right? So means when you are going to combine this kind of procedure, you are going to get 9 tuples. You are going to get 9 tuples, but actually we need to get only 3 tuples. We need to get only 3 tuples. Then this situation I can call it as, or this combination, this combining of 2 tables into single table, this combination I can call it as lossy decomposition. Lossy decomposition, right? So means if I am going to say that R1, R2 are decomposed as lossy decomposition, what does the meaning of this one? It may produce spurious tuples. We can say that it may produce spurious tuples. Spurious tuples means what? There will be a meaningless data. Meaningless data, then I can call it as spurious tuple, right? So when you are going to perform any kind of a decomposition in such a way that it is going to generate spurious tuples, then I can call it as lossy decomposition, right? Yes. So because if you are going to get invalid, it doesn't have any meaning, so there is no use of it. So you have to make sure that it has to produce always lossless decomposition, right? Yes. So this is for test criteria, right? So for example, I am trying to split this JKL table into another format. Like for example, I am decomposing into 2 tables where one table contains JK and another table contains KL are the attributes. Right? Guys, here you got 9 spurious tuples. It is because of there is no common column. If I am going to make some kind of a common column, like here JK and KL, assume the data is A1 B1, A2 B2, A3 B1. Similarly, B1 C1, B2 C2, B1 C3. If I am going to apply natural join between these two, what data you might get? You might get JKL only are the resultant relation, but the final tuples are maybe vary, right? So star means what? It's going to apply the equal to operation on both common columns. So it is going to perform B1 B1 and this B1 B1, right? So you are going to get A1 B1 C1. Similarly, A1 B1 C3. Similarly, for A2 B2 C2, you are going to get only one data, as B2 is contain only one particular column. For coming to A3, A3 B1 B1 C1, A3 B1 C3. So you are going to get 2 more tuples, right? So in this particular kind of joining also, in this particular kind of decomposition also, after combining these 2 tables, you are going to get again lossy decomposition, meaning that it is going to produce again meaningless data. Why it is producing the meaningless data? Here we are trying to combine 2 common columns only. If you are able to observe clearly, here the K contains duplicate data. So the point I can conclude here is, whenever you are trying to combine without common column, you got here 9 tuples. If you are going to combine with common common column, so you are going to get somewhat less tuples compared to the earlier case, right? So there is a chance of getting more tuples also, but this is one case, right? So in order to avoid the spurious tuples, you can able to take the common column as primary key. Then it can definitely eradicate the spurious tuples, guys. Why? Primary key means it contains a not null and it is going to be an unique key column. Means it contains only unique data, right? Now suppose for example, I am trying to make one table is J and it contains L attribute also, and another table which contains L attribute and K attribute. Now if you are able to observe, if I am trying to combine, see, observe A1 C1, A1 C1, A2 C2, A3 C3, and for L and K, C1 B1, C2 B2, C3 B3. If you are able to combine these two into a single table, final resultant relation contains JLK, good, JLK. Okay, fine. If you are able to combine, so C1 C1 natural join if you are going to apply, C2 C2, C3 C3. So you are going to get the data like A1 C1 B1, A2 C2 B2, A3 C3 B3. That's it. So you got only 3 tuples. These 3 tuples are actually matched with the actual data. This kind of decomposition, I can call it as lossless decomposition. Means there is no loss of data. Meaning that in DBMS you can say that there is no invalid data it is producing. So you can call it as lossless decomposition. So when you are trying to performing some kind of decomposition, any kind of decomposition, whatever the way you are trying to do, make sure that it has to follow lossless decomposition property. Means it should not generate any kind of spurious tuples, right? Yes. So now, for example, if somebody generated various kind of sub relations like R1, R2, R3 and so on, Rm from a relation called R, where it contains the attributes are like A1, A2 and so on, Am. Right? When I can say that it's a kind of lossless decomposition, when I can say that it's a kind of lossy decomposition. Right, guys, what we did here, we did made simply natural join on all the relations like R1 and R2 natural join. If I am going to do, if it is going to be equal with the actual data, I can call it as lossless decomposition. That's what I would like to write, right? So if I am going to perform natural join over that sub tables, sub relations, R1 natural join with R2, R2 natural join with R3 and so on, natural join with Rm relations. If the resultant relation is matched with actual relation, then I can say that it is lossless decomposition. Suppose if R1, R2, R3 and so on, Rm are going to produce more tuples than the relation R tuples, then I can call it as definitely lossy decomposition. So with the help of previous examples, you can able to clearly understand this definition, right? So this you have to make it understood. Okay, so here lossy means it's not only about losing the data, it's also about a kind of case where you may get invalid data, right? For example, if I am going to have 2 tables, again one schema is J, K and L. This schema I am trying to split into 2 schemas where K is the candidate key. Now can I able to split this table into 2 tables where candidate key is follow? Yes. If I am going to say that it's a kind of a candidate key, it definitely is not going to contain any kind of duplicate data. So I won't get any kind of spurious tuples when you are going to generate or when you are going to combine 2 tables. So I can say that this is going to generate definitely lossless decomposition. Okay guys, so but basically how can we find or how can we test whether the given relation is lossless decomposition relations or lossy decomposition relations? Guys, basically with our illusion, can we able to do, see, observe, if I am unable to find I'm able to find any kind of common relation between the two relations R1 and R2, can I say that it's definitely going to produce lossless decomposition? Yes. Even if I am going to find any kind of common attributes between the two relations, if that common attribute is not a candidate key, I can definitely say that it is a lossless decomposition. Yes. When I can say it is lossless decomposition, if I am able to find a common column between the two relations, and that common column should be a kind of a candidate key, then definitely it is going to be lossless decomposition. Lossless decomposition, right? So here we are trying to think about like common property, right? So this kind of procedure, I can call it as intersection procedure, right? So one way of solving to define or to test whether the decomposition relations are lossless decomposition or lossy decomposition, I can follow an approach called intersection method approach. Intersection method approach, right? What does the intersection method approach is going to define? Like for example, let me take a simple example. There is a relation called R where it contains data like A, B, C, D, E, F are the attributes, and assume that there is a table relation, sub relation called AFC, right? So if I am going to say simply in terms of representation, decomposed tables are AFC, CD, BE and AB. BE and AB. Assume that A is a candidate key here. A is a candidate key, and B is also kind of a candidate key. B is a kind of a candidate key, right? Yes. And if I say C is also kind of a candidate key. C is a kind of a candidate key, right? So if I am saying that A, C, B are the candidate keys, A, C, B are the candidate keys, can we able to define whether the decomposition is lossless decomposition or lossy decomposition? How can we do that? See, for example, what I will do now, I am going to give some kind of namings as R1, R2, R3, R4 for the subrelations. First, what I will do, I will try to take out two columns, or sorry, I will try to take out the two relations where there should be a common column and one of them should be a primary key, or one of them should be a candidate key. See guys, every candidate key is a, we can say is a candidate key. Among those candidate keys, we will select one of the smallest set which contains the less attributes as a primary key. Okay, so for time being, what I will do now, I will try to select R1 and R4. If we take R1 and R4, AFC, AB. So among these, A is a candidate key. So if I are able to observe, A is a one table contains a key as a candidate key. If I am going to combine them into a single table, is not going to generate any kind of spurious tuples. So what I will do now, I will try to combine A, B, C and F. A, B, C and F, right? Very good. So now we got a new relation A, B, C, F, right? So which means I have done with R1 and R4. Now can I able to combine? See, if I am going to say that A, B, C, F generated, A is a candidate key. Now can I able to do it with either R2 or R3? You can do, right? So for example, I am trying to take this resultant relation with R2, right? So the R2 is here CD. You know already C is also a kind of a candidate key, so there is no problem. I can able to simply combine into a single relation because it's a kind of common attribute, and this is also kind of a candidate key. So you are going to get A, B, C, D and F. Among those, the candidate keys are A and C. Now can I combine this? So this is also done. Can I combine this with the B, which I can say it as R3, where B is also kind of candidate key. If I am going to combine these two, you are going to get A, B, C, D, E, F, right? Which is equivalent to the actual relation. Which is equivalent to the actual relation. I can call it as this kind of decomposition is definitely lossless decomposition. Lossless decomposition. See, so the main heart here is we are simply we are going to simply finding the two relations. One relation is R1, another relation is R2, and if you are going to make any kind of attribute as common attribute, and that common attribute should be compulsory a kind of a candidate key, then we can able to create new relation with the attributes of R1 union R2, right? So this is the procedure what we are doing for intersection method. Okay, fine. So let's take a simple example, another one using with the help of intersection method only. For example, there is a relation called R which contains attributes are like this: A, B, C, D, E, F, G, H, I, J, and the set of decomposition tables are A, D, E, D, I, J, B, F, F, G, H, A, B, C, and assume that I am writing simple note. Assume that common column is a candidate key. Column is a candidate key. Now try to solve. How can you do this? See, so they confirmed that every common column is a candidate key. Now if I am going to combine two tables, definitely is not going to produce any spurious tuple. So here, if you are able to observe, D is the common column. Can I combine these two? Yes. If I am going to combine, you are going to get non-spurious tuples. So actual data you are going to get A, D, E, I, and J you are going to get, right? Now can I combine this with B, F? No, it is not possible to combine for time being right now. So can I take F, G, H? F, G, H also is not possible now, right? So F, G, H is also not possible now. Now can I take A, B, C? If I take A, B, C, and if I are going to combine these two tables into a single table, why I can able to combine these two tables into a single table? They said like the common column is definitely going to be a candidate key. So in this scenario, this case I can call it as candidate key. Now, so the resultant relation contains A, B, C, D, E, I, J. Now this is new relation. Now this new relation can I able to combine with B, F? Yes. So I can simply take this one combined with this one. You are going to get a new relation, that is A, B, C, D, E, F, I, J. Now this is new relation. This new relation can I able to combine with F, G, H? Yes. So I can have a candidate key called F according to their assumption. Yes. So if I am going to combine these two into a single table, I can get A, B, C, D, E, F, G, H, I, J. So this is my resultant relation, right, guys? So observe, if the resultant relation contains the attributes are there, if those attributes are matched with actual table attributes, then I can say that this kind of decomposition is definitely lossless decomposition, right? Yes. So let's see one example where the decomposition can be a lossy decomposition. For example, the relation is ABCDE, where it contains the decomposed tables are one is AB, another one is CD. Guys, tell me, is this a lossy decomposition or lossless decomposition? Definitely, it is a lossy decomposition. So, on what basis I am trying to say? because there is no common column, first thing. But before going to tell it is a lossy decomposition or lossless decomposition, first, is it a valid decomposition? No. So the decomposition itself is invalid decomposition. Why means the actual table contains the attributes are A, B, C, D, E, but the decomposed table's combination contains the attributes are only A, B, C, D, which means that I am lossing D, comma E column attribute data. As I am lossing the direct attribute data, I can say that it is kind of invalid decomposition only. So I can say it is lossy decomposition. Okay, fine. So for example, if my decomposed relation will be like in the form of AB, comma CDE. Now, is this decomposition is first a valid decomposition? Yes, definitely the decomposition is valid decomposition, as the result as the all decomposed relations contains all the attributes. But is it a lossy decomposition or lossless decomposition? It's going to be a lossy decomposition. The reason is there is no common column. When there is no common column, it is going to definitely generate spurious tuples. That's the reason I can say that it's a kind of lossy decomposition. Guys, so if you are able to observe, so in this kind of intersection method approach, we are trying to find out the common column, and if the common column exists, and we are trying to check that whether it is a kind of candidate key or not. As in the earlier example, they said directly they are common columns, so we are not checking. So as it is a common candidate key, and then I can say that I can able to combine those two relations. Finally, I am going to repeat this process. Until all the relations done. Until all the sub relations combine, right? So now, if it is going to get all the attributes, then I can say that it's a kind of lossless decomposition. Otherwise, I can say that they are lossy decomposition, right? Based on two criteria, you can able to know that, right? But the thing here is, when we are going to follow this entire approach, certain situation there is a chance of producing errors. Right? There may be a chance of mistaking of finding whether it is a candidate key or not. Right? See, for example, let me take a simple example with help of intersection method. There is a relation called R relation with the attributes A, B, C, D, E, G, and they have given set of functional dependencies. Functional dependencies are AB determines C, AC determines B, AD determines G, B determines D, B determines A, E determines G, and the decomposed relations are ABC is one decomposed relation, ABD is one kind of decomposed relation, EG is one kind of decomposed relation. Guys, so here we have to check whether it is lossy decomposition or lossless decomposition. So basically what we can do, we can go with this intersection method and we can able to define. Right? So what does the intersection method will do? Assume that this is R1, R2 and R3. R1, R2 and R3, right? So in this intersection method approach, we are going to simply take two relations. One is ABC, another one is ABD. Now, what are the common columns available here? Common columns available here. AB is one common column. AB is the common column between these two relations, right? Yes. So when these two are common columns between the relations R1 R2. Earlier what they did, they will simply define that, assume that those are candidate keys. Assume that those are candidate keys. So without seeing, without observing whether the common columns are candidate key or not, we are going to simply merging them into a single data A, B, C, D, E. Like this we did. But here the case is different. They haven't mentioned whether they are candidate keys or not. Right? So what you have to do? You have to find out the common columns or candidate keys or not. You have to find out. So if I take AB as the common column, if you are going to find out the closure, guys, you know, one of the advantage of closure property is we can able to define whether it is a candidate key or not, right? If I am going to find out AB closure from the given set of functional dependencies, am I going to get AB? Yes. From AB I can get C. Right? If I are able to observe, so I can continue further also. AC determines G. See, if you want, I can continue. AC determines G. Sorry, AC determines B. AC determines, as this AC determines B. Again B determines A. B determines D. Like that. So as B is already there, so I no need to write again. Right? So B determines D. B determines A is already there. As AD is there, AD determines G is also possible. These are possible, right? So yes, these are the possibles for AB closure. But the thing is, what is the meaning of a candidate key? If it is going to be itself identify at least one of the table, AB closure is ABC, right? ABC. Now I can say that here AB is a candidate key. Why it is a candidate key? It can able to define all the attributes. But can I say that AB is a candidate key in this particular relation? No, because if it is not able to derive E, so I cannot say that it is a candidate key. It's a candidate. But anyway, our requirement is I need to find whether it is a candidate key or not. As they are candidate key in one of the relation, I can able to simply combine them into a single table. Right? So the resultant relation contains A, B, C, D, E. Right? So the point here I would like to introduce one important point is, in the intersection method, when R1 intersection R2, it may generate, if I am saying that one of the attributes is a candidate key, it may generate either R1 or it may generate R2. When it is going to be generate R1, if candidate key attribute is present in R1, then it can generate R1. If candidate key present in R2, it can generate R2 relation. Right? That is what I said, right? As candidate key is present in R1, if I say that this is R1, this is R2, it can generate a relation R1. It can generate a relation R1. That's what I am trying to impart, right? This is important. Okay, fine. So here we got the combination of ABCD. Now, right? AB closure fine. Now, is there another relation is there? Yes. Now, EG is there. Right? Now, try to find out the common column. The common column is E is the common column. Right? But if you got clarity, E is a candidate key, we can able to combine. But we don't know whether it is a candidate key or not. So we have to find out whether it is a candidate key or not first. If I find out the E closure, you will get EG. From this particular relation, right? Means it can able to generate one of the table completely. As it is going to able to generate one of the table completely, E is a candidate key. If E is a candidate key, I can able to combine it into a single table. A, B, C, D, E, G. Right? Now, the resultant relation contains A, B, C, D, E, G, which is equal to the actual table attributes. Now, I can simply say that this decomposition is lossless decomposition. But the thing is, guys, here, if at any particular moment of time, if you are able to find any mistake, that may lead to errors. Right? To overcome this drawback, we are moving for one more kind of method, that is tabular method, where this method is somewhat lengthy approach, but it definitely eradicate the errors. That we'll see in the